Hi everybody, welcome back. So today we're going to talk about model dependence. We're going to talk about defining model dependence, detecting model dependence, and correcting for model dependence at least to some degree. So what the heck is model dependence? First, a qualitative definition. So think about this. It takes a long time to design research. Let's suppose you took 2 years. That's a reasonable amount of time. You convinced your advisors and your confidants that this was the right thing to do. You produced the design. You then convinced the government or a community or some village or all your respondents to collect the data. You then went and collected the data, which is an enormous undertaking. You got it all back. You spent months cleaning it, getting it all in the right columns. You now have the first data set from this project that you've spent a significant fraction of your graduate career and frankly of your life working on. Those data are now in your computer. They're now in the right columns. You can now run the first analysis. So you're in your office, you're in your room, whatever it is. There's one light over your head, the door is closed. You're ready. You clean the last datum. You push the button, you get the results. Okay, so you get the results. There's some quantity of interest. Hopefully you all simulated to get exactly the quantity of interest you want with the right level of uncertainty. So you get everything all set, right? And once it's all set, you get that result. You get that estimate. What do? You have the estimate after 2 years. Do you just go publish it? No way. There's no way you're going to go publish that. You're going to run it again after you adjust for missing data in a different way. And then you're going to run it again after you adjust for the sample frame in a different way. And then maybe you're going to correct for measurement error. And perhaps you're going to change the specification, the functional form, the stochastic component, the way that you estimate the model, all kinds of different things. You're going to do diagnostic tests. That's going to suggest other things to do. You're going to run 500, 5,000 different analyses, and then from that you're going to choose one. Okay, all that is reasonable. All that follows best practices in a sense, right? Because you're exploring the data. You're not going to be fooled by some miscoding or outlier or something like that. Okay, but suppose that your results are just completely different when you make small changes in the model. Now, if they're big changes that you can defend, well, of course, it's perfectly fine to choose not to use a specification if that specification doesn't make sense. But if you get to look at the results and from the results actually decide what makes sense, well, then we sort of know that you're going to wind up biasing things in your favor because that's what humans do. And you, unfortunately, have this problem. You are inadequate because you're human. But I'm not so worried about you. I'm worried about the other guy. You're reading that article, and you see this one beautiful set of results. Maybe even there's 3 or 4 sets of results. Maybe even there's 5 columns with the quantity of interest in the first row and the other rows being other variables maybe which were included or others indicating other specifications. So now you have 5 estimates of the quantity of interest. But even that person undoubtedly ran dozens and dozens and dozens of others. How do we know that what you're reading in that paper is not merely a proof, an absolute proof, that it is possible to find results consistent with your hypothesis, rather than the data really conveying what is being written up? How do you know that? That's model dependence. Model dependence that we care about is when big changes in the results happen from small changes in the model. And by small, I mean ones that you really don't know whether they're right one way or the other. Do you include that interaction term? Do you include that covariate that you really didn't have strong sense of whether you should put in there? Is it a logit or a specification or a probit specification, et cetera? So that's model dependence. Model dependence is an enormously important area. And it is one that tends to be neglected, but it's not one that we're going to neglect. Okay, so we're going to talk about model dependence. We're then going to work on ways of correcting model dependence. In particular, we're going to use a technique called matching, which probably should have been called pruning, which basically just discards some data in a very specific way. We've talked about that a little bit. We'll get into it in more depth in this lecture, and then in even more depth in a way that you could use in the next set of talks. Okay, so let's get started. So the first I'm going to talk about model dependence. I first studied this with my former postdoc, Langsha Zheng, who went on to be a professor of political science at UC San Diego. Langsha and I wrote a paper, and we had some great applications, or we thought they were great in international relations, and we sent them off to International Studies Quarterly, quite a good journal. And the editor of the journal said to himself, you know, there's a lot of technology in here, because there was a good amount of math in there, more math than was common in that journal or in that field. And so he, without our knowledge, called up the editor of Political Analysis, and they made a deal. And the deal was, Gary and Langsha, if you guys could rewrite this paper twice, once for my journal and once for Political Analysis, where most of the paper actually overlaps, that would be great. And with more examples in ISQ and more of the math and the proofs in PA. So that's what we did. It was a pretty unusual situation. It actually happened to me once before. It's always good to try to publish in the substantive journals, but sometimes you go just a little too far. So you can court me. There's software that does everything that I'm going to describe here today and in the next talk. What if is what Langsha and I came up with that helps you detect model dependence very easily without even running any models. I'll explain how that works. Match It will help you run matching procedures, as will CEM, and Zelig is a way of estimating quantities of interest, as we've talked about. So this is the website where you can get it. They're all available at my own website as well. Okay, so counterfactuals. We've talked about counterfactuals. There are three types. Model dependence will be relevant to all three types. The first type is forecasts, and the counterfactual is just, it's not the year 2025. What will, for example, mortality rates be in 2025? Second, what about what-if questions? What would the United States have been like if we had not invaded Iraq, for example, or if there had been no pandemic? What would it have been like? It's reasonable to ask those questions, even though there's no direct evidence of it. There's indirect evidence of it, and we'll certainly use that evidence to try to make inferences about it. But it is, of course, the definition of a counterfactual question. And third, there are causal effects. As we've discussed, a causal effect is the difference between a fact and a counterfact, right? So it's the value of the outcome variable, perhaps that where that unit had treatment, minus the value of that outcome variable if that unit had not received treatment, or the average of those types of treatment effects over certain subsets of observations. So we're going to focus on those counterfactuals, those three types. Counterfactuals are pretty much define most social science research. Okay. Here's a data set. Horizontal axis is x. That's our predicted value. The vertical axis is y, our outcome variable. This is a totally constructed data set just to emphasize the points, but it's not wildly unusual. So here's a little data set, and now I fit a linear model to this equation, and I fit a quadratic model to this equation. And there's several things that are worth paying attention to. We're going to look at the prediction of y starting with x equal 1.5 and then x equal 5. So I want to compare those two. But the first thing that you should note is that the linear regression fits these data pretty well. The quadratic regression fits the data pretty well. Which one fits better? Seems pretty much the same to me. But if you have a look at that, they're both fitting well. Now let's look at the prediction at 1.5. What's y going to be if x is 1.5? If x is 1.5, you go up here. It doesn't really matter which model you choose for your estimate. It's just somewhere in the middle of those points. Then you go to the left. That's your prediction. If you're predicting at 5, then and you choose the linear model, then you expect y to be about here, right? To be about 10. If, however, you're predicting from y and you decide to choose the quadratic model, then you go all the way up to here, which is 2 or 3 times larger. So that means the answer depends enormously on your choice of the statistical model. In fact, this linear model is a linear model of a regression of y on this x in a constant term, that's all. This is just one more variable. It just has the square term. It just has x squared added to it. So it's almost the same model, has one little additional wrinkle, and that consequence is huge for this predicted value of x, and inconsequential for this value of x. That's the key insight of this whole thing. Now, which model would you choose? Right? How do you choose one of these models? Do you want to pick r squared? Right? Which model fits better? Or some test? Right? Now, if somebody came along with a test and convinced you that mathematically that test was a good test for determining whether one model fits data better than another, great. But if you look at those data, if you look at the data just to the left of me, right, you look at those data and you ask yourself which model fits those data better, and someone comes along with a test to tell you that one's better than another, what do you say to them? Get lost, right? I mean, who really cares, right? Those models fit the data essentially as well. If they're picking up one little blip in the data, that's not an important thing. The real question is there really a difference? And they fit the data essentially just as well. So you could use theory. There could be a theory. I've made up these variables. They're called x and y. They don't have any substantive meaning in this graph. But you might have some theory that tells us that the relationship really should be quadratic, in which case, fine, you choose the quadratic. But we don't usually have that kind of theory in the social sciences. If you do, great. If you don't, this is the situation you're in. The bottom line is, you may have a data set. The data set may be very informative for some questions, but for other questions, it may not tell you anything. And answers to some questions just don't exist in your data. It is really important that you know what questions you can actually answer from your data set and which questions cannot be answered from your data set. So that's what we're going to focus on today. This is the same for all three types of counterfactuals. What if questions, predictions, and causal inferences. Some questions don't exist in the data. If we asked what would happen to presidential approval if inflation went up by 2 percentage points, we could answer that question on the basis of the data, where the data comes from prior American history. If we asked what would happen to the American president's approval rating if inflation went up by 400%, as has happened elsewhere but has never happened in the US, then would you trust the data from the US to make an inference there? No way. It's way too far from the data. Okay. So I'm going to give you one insight from a mathematical proof that we have in this paper. You can just take the assumptions and the results. You don't need to see exactly how the math worked if you trust us, but you should read it when you go look at the paper. For starters, I want to put things in context, and the context is a model-free inference. So suppose we're interested in estimating the expected value of y given x equal to some value little x. So the mean of y for that value of x. So a model-free inference of that is just the average of y for a whole bunch of values, a whole bunch of units that we ideally would find with value x. So if you can do that, you just take the mean. There's no model, there's no functional form that could be wrong. It's just the mean. Okay, so now I'm going to make some assumptions. Then we're going to give you results. These are assumptions for model-based inference to contrast with a model-free inference. So first, a definition. The model dependence at x is the difference between predicted outcomes for any two models that fit about equally well. Okay, so so you take two models, they fit the data about equally well, just like the graph on the previous page, and then you see whether they make a big difference, and the degree to which they make a difference in the outcome for a given counterfactual, right? All this is defined for a given counterfactual. In the graph on the previous page, a counterfactual was just a value of x. Where a factual would be you'd choose a value of x that would land on one of the data points. But right, so that's the key thing. So that's the definition of model dependence. Second assumption is the functional forms that we're talking about. In order for me to give the result that I'm about to give, I have to make one assumption, and that is the functional forms can't be too wild. which roughly speaking means they're smoothish. Okay, there's a mathematical version of smoothish. That's a little more formal than that word, but you can just think of it as continuous. There's continuity. It's not too wildly jagged. Okay, so if we make those assumptions and we run a model, and we use that definition of model dependence, then here's the results. It's quite simple. The maximum degree of model dependence, it could be smaller, but the maximum degree, the degree that the type of model dependence we should worry about, which is the maximum model dependence, is a function of how far the counterfactual is from the data. And you saw that in the graph on the previous page when we were making an inference about 1.5, x equal 1.5, which was in the middle of a bunch of data. It wasn't very model dependent because all the models fit the data just as well. When we made an inference far from the data, then answers tended to be much more model dependent. And so this is the result. The maximum degree of model dependence that we could find is a function of how far your questions are from the data. And it's sort of no surprise, right? Of course, you're going to want your results to depend upon the data, not depend upon extrapolation far from the data. Okay, so let's now think about how we measure distance from the data. So we could do it directly. We have a mass of data points, and we could look at it on the graph that I showed you a couple of slides ago. We could instead calculate quantitatively the average distance from a counterfactual point to each of the points in the data set, or to the nearby points in the data set, or something like that. And in these two papers that Langsha and I wrote, only one of which you need to read, right, because they overlap. In these papers, we came up with quantitative measures of the distance from a counterfactual point to nearby points in the data set. And you absolutely can use those. There's lots of them. There's a couple in the paper that we recommend. But there's a lot of ways of doing them. And so what we did is we thought about what's the simplest measure of distance that would work reasonably well. So what we came up with was a dichotomous measure of distance, which is far, near. That's it. Okay, and here was obviously it's simplistic or simple, but it tends to work reasonably well. So the measure is the convex hull. It's exactly what's on the slide over there. Or maybe it's over there. Anyway, wherever I put myself when I put these videos together, that's exactly where it is. And let me explain what the convex hull is. You may have heard of this term before. Here's a histogram of one variable at a time. The convex hull is the minimum point and the maximum point. The minimum point and the maximum point. And all we need is to know for any counterfactual point, is the counterfactual between the minimum and the maximum, or on the outside over here or on the outside over here. If it's on the inside, if it's on the inside of the convex hull, it's called an interpolation. If it's on the outside, it's called an extrapolation. If it hits one of these points exactly, it's neither. It's, you sort of get it exactly. But even if it hits it exactly, those points are, any one of the data points in a real social science data set has measurement error and sampling error and stochastic error. And so we wouldn't trust one point exactly. So pretty much we just summarize all counterfactual questions as either interpolations or extrapolations. Interpolations being in the middle, extrapolations being on the outside. Okay, that's one variable. That's if you only have one explanatory variable. What if you have more than one explanatory variable? It turns out there's a definition of convex hull for that. So on the right here, I have x1 this way, I have x2 this way, no y, right? There was no y here either, there's no y here. So this is x1 and x2. And then if each of the dots in the graph is let's say the graph is a board, and each of the dots is a nail that we nailed into the board, and then we took a big rubber band and put it around the edge. This outline, this polygon on the outside, is the convex hull. So that's the whole thing. It's convex rather than, it never goes in. It always is either flat or goes out. So that's the convex hull. And what we say is any counterfactual, which in this case is defined by the value of two explanatory variables. In previous sets of slides, we defined the counterfactual as our choice of x's, x sub c. And c, I said, was choice. Well, it could be c is our counterfactual. And so if the values of xy, of x1, x2, not xy, wind up in the middle here, inside the polygon, inside the convex hull, we're going to call that interpolation. If it winds up outside, anywhere outside, we're going to call it extrapolation. And the key thing is, interpolation is not so model dependent. Extrapolation is quite model dependent. Works mathematically for any number of explanatory variables. So if we had 3 explanatory variables, we'd have x1 this way, x2 this way, x3 this way, and this point would have a value on all 3 variables. And this point would have a value, and this point would have a value, and this point, and this point, and this point, and this point. And if we had all those points there, and we took a sheet of saran wrap, and the point stayed still, and we wrapped it around it, and we got a hairdryer and blew it all, right? We get a 3-dimensional polygon, and that would be the convex hull. We can do 4 dimensions also, but we need like a whole lot of jello, which gets complicated. But we can do more and more. Actually, it works mathematically with as many dimensions as you like. There's software to figure out whether a point is inside the convex hull or outside. For 1, 2, or 3 dimensions, it's pretty straightforward. For 20 dimensions, the hull itself is a very complex mathematical object, and it's absolutely enormous. It's so large that you would never be able to print out the directions to construct it. It would just take longer than there is paper, basically. So you couldn't actually do it. But we don't really need the whole convex hull. We only need, for those 20 variables, and the data set defined by those 20 x's, those 20 explanatory variables, we need to know where the convex hull is. But remember, we only need to know that because our question is, does our data point, which is one point, one value of all the explanatory variables, is that inside the convex hull or is it outside the convex hull? So it turned out to be impossible or impractical to define where the convex hull was in any number of dimensions, but we figured out, Langshan and I figured out, that we could take one of these points and just ask the question of our software, is it inside or outside? And what if this nice piece of R software will tell you. It'll say, yep, it's inside, it's an interpolation. Nope, it's outside, it's an extrapolation. So that's pretty much the whole thing. Now, just to be clear, this is a dichotomous measure of distance, right? So it's not perfect. You could be just outside the convex hull, and that, if you're just outside the convex hull here, maybe, even though we would define that as an extrapolation, maybe that's not that far from the data, but sometimes there's holes in the data, inside the data set that might be far from the data. There's absolutely, it's a dichotomous measure, right? So it's a crude measure. It just seems to work pretty well. Okay, they tend not to be giant holes in data sets. When we make an extrapolation, we tend to go pretty far. So, and in any event, it's an indicator. You could measure it with actual measures of distance if you like. Okay, so here's an example about model dependence. Now, this example comes from a replication that Langshan and I did of a paper by Michael Doyle and Nick Sembanis. It's a great paper. It appeared in the American Political Science Review around 2000, or in 2000. It is about a data set of 124 post-World War II civil wars. The dependent variable is peace-building success. So they're trying to figure out how, let me go one more step, which is the treatment variable is how the United Nations, when they send in multilateral peacekeeping forces, what the causal effect of that? Does that improve peace-building success or not, right? So this was a very important article because they were the first to quantify this process. And there's been subsequent research that's built on it, and so it was a good thing to do. In fact, it wasn't just an academic piece of work because Michael Doyle, when he was finished with this paper, went on from academia to the United Nations to run the office that decides whether to send in multilateral UN peacekeeping missions. So not merely an academic argument. So quite an important paper. Anyway, so we replicated this paper. They're interested, remember, in whether or not you send in the troops, and whether they're successful. They had a whole bunch of control variables because if you send in the troops sometimes and you don't send in the troops other times, and you only send in the troops when things are going to go well, and you don't send them in when they're not going to go well, then you could be fooled into thinking that there was really an effect. And so they were right to control for lots of characteristics of the wars, how severe they were, how long they were going, the development status of the countries, a whole bunch of things. They had a counterfactual question. Their counterfactual question was really a set of 124 counterfactual questions. They lose 2 of the observations later on, so it's really 122 observations. They want to know for each of these observations, what would have happened if the UN had made the other decision? So if the UN had decided to intervene, they want to know what would have happened if the UN didn't intervene. And for those of the 122 post-World War II civil wars, if the UN didn't intervene in one, what would have happened if the UN did intervene, right? Great question. So they ran a logit model that controlled for their control variables, that looked for the effect of the treatment variable on the outcome. Their question was whether the UN was successful and how they were successful and when and why. Our question was not that. We're not interested in, of course we're interested in the substance, but that's not why we're here today. We're here to talk about the methods. And so the question is, how model dependent are the results? That's what we really want to know. So the first thing we did is we calculated the percent of counterfactuals in the convex hull. Seems like a straightforward thing to do. There are 122 of these counterfactuals because they're going to switch each one. And so we wanted to know how many of these were inside the convex hull, were subject to relatively little model dependence. And the answer was 0, which means all of their counterfactuals were model dependent, all of them. Well, that's pretty interesting. So we thought, well, that means we know before we estimate any models. Remember, I've described the dependent variable here, but when we did our analysis to figure out whether a counterfactual is in the convex hull, we fed into what if a matrix of explanatory variables, the data, and then one more value of each of the explanatory variables, which is the counterfactual. That's all what if ever sees. It doesn't see the outcome variable. And it determined that all 122 counterfactuals, every one of the points we fed in, were not in the convex hull, and therefore there was model dependence without seeing the dependent variable, which is sort of pretty cool, right? Without seeing the dependent variable, we know that if we run a model, some model, there will be model dependence. Now, not always model dependence, because our proof shows the maximum degree of model dependence is a function of distance from the data. So we thought, let's go look for an example, right? Let's go see how hard do we have to look before we find the model dependent result, okay? So now I'm going to show you 2 logit models that have apparently very similar results, but aren't really. Again, this is the effect of multilateral UN intervention on peace building success. Now, I've told you again and again, don't present results like this, okay? But you need to give me a break because I used the presentation method of the original authors, and you need to give the original authors a break because they published this paper 20 years ago, pretty much the same, in fact, it was the same year that we published our Clarify paper about how to interpret results. So they did a great job for the time. In any event, what they published was this model. It's a logit model. Here's a bunch of explanatory variables. Here's their coefficients, their standard errors, their p-values by Neyman Pearson hypothesis testing. This is a constant term. Excuse me. This is 122 observations. Their log likelihood value, which is only relevant when you're comparing different specifications on the same model, but I'm going to have another model here. This is something called pseudo R squared, which is sort of like the proportionate change in the log likelihood if you run the model with no covariates, just the constant term, and then with all the covariates. It's not a particularly interesting number by itself because even though it can only be on a scale it only goes on a scale from 0 to 1, it's still a relative number just like the log likelihood, so not especially important, but in any event, it may give you a descriptive feel for what's going on. So that was their model. how would you interpret this, right? You should go back and simulate. That would be the best way to do it. But if you have a look at this, remember I gave you a rule of thumb. So if somebody slid this onto your desk and asks you how do you present these, do you know how you present them? Do you remember? That's right, divide them all by 4 and roughly interpret them as linear regression coefficients. Okay, so that's the quick way of getting a sense of what's going on. All right, but the substance in this particular case is not what we're interested in. What we're interested in is model dependence. And I would like to not just do it in a general sense like we did with the convex hull, but I want to find a specific example. So we had to modify the model. What modification could we choose? It could be anything. We thought it would be reasonable to start with their model, which they called an interactive model. And their qualitative theory of what was going on in peace-building success was an interactive theory of peace-building success. That's how they described it. So we thought, since interaction was so important to their theory, that we would use an interaction and add it to the model. So that was the only change from the original model to our modified model, was this line called an interaction. That was the whole thing. And this is the coefficient, and that's the standard error, which is, the coefficient's more than twice the size of the standard error. Therefore, the p-value is small. So maybe it should belong in there. But in any event, there are 2 models. If you look at this number and this number, they're not that far apart. This number and this number, they're not that far apart. This 0.006 and 0.006, this 1.2, this 1.0, this 0.062, right? So they differ, but they're not wildly different, okay? So roughly they're giving the same message maybe. Let's have a close look, okay? So on the left-hand side, I'm going to show you the fit of the model. On the left-hand side, I have the proportion of, I have the probability from the original model on the vertical axis, and I have the probabilities from the modified model on the horizontal axis. Okay, and as you can see here, the predictions fit very well. So just to be clear, what we did is our x sub c, our choice values of x's, was for each of 122 predictions, we used the observed values of x. That's it. We just stuck in the observed values of x, calculated a predicted value under the original model, and then under the modified model, which also had an interaction. In each case, we produced a predicted value. For a regression, it would just be a y-hat. It's logit, so you plug in the value, you get out a prediction. In almost all cases, there was essentially no difference between the 2 models in sample predictions. There were a few differences. This one was different, this one. And if this was a substantive analysis, if what I'm doing right now is a substantive analysis, we would of course drill in and figure out, well, which civil war was that? Why was it so? Why did the 2 models pick up different features and send the predictions in a different way? However, for now, the main point of this graph on the left here is just that the fit of the models is basically the same. That's the whole thing. Okay, so let's go look at the model on the right, at the graph on the right. The graph on the right is pretty much the same as the graph on the left, except they're now for counterfactual predictions. So now what I did is we put in all the observed values of the explanatory variables. But for the Treatment variable, if it was a 1, I made it a 0, and if it was a 0, we made it a 1. So that's what we did here, right? So we're now predicting under counterfactual. If they intervened, we tried to predict the probability of peace-building success if they didn't intervene, and if they didn't intervene, we figured out the probability of peace-giving success if they did intervene. And although these in-sample fits are almost exactly the same for the 2 models, here they're massively different, right? This is basically a spectacular example of model dependence, where if, for example, the original model says there's a 0.5 probability of peace-building success, the counterfactual prediction, the same counterfactual prediction from our modified model ranges from nearly 0 to nearly 1. You see that? Right? You would expect them all to be on the 45-degree line if they were giving the same prediction, but they're giving massively different predictions. They're not completely different in every case, of course, but they are hugely different, okay? So, in fact, it's hard to find an example of bigger model dependence that has such substantive meaning. In this case, every one of these data points has deep substantive meaning, because every one is what would have happened if a major event in the world changed, right? If the UN did intervene or didn't intervene. So this is a good example of model dependence. Why is it that there was so much model dependence in this case? Why is it? Well, the UN doesn't intervene at random. That's why, right? The covariates that, Doyle and Sambanis appropriately tried to control for, and they did control for it in their logit model. It turns out that controlling for them made the counterfactuals go very far outside the convex hull of the data, because there are no cases like the cases where there were interventions, but all the values of the explanatory variables stayed the same. That's really the thing. The UN intervenes for a reason as a function of the variables that they were clever enough to measure. But because of that, you can't just swap one of the explanatory variables, that is the treatment variable, and hope that you can find another value of another unit where all the treatment variables, all but the treatment variable are the same. So that's the reason why it was so model dependent, because the UN intervenes for a reason. Unfortunately, they don't intervene at random just for us. If they were doing this for substantive, or for our own methodological purposes or our own substantive research purposes, they would intervene at random or when we told them to. But fortunately for the world, they don't do that. Okay, so we've talked about model dependence. We've talked about defining model dependence, evaluating it, figuring out when it's going to be there. Now we're going to talk about what to do about it. Matching is pretty much the thing that we're going to do about it, aside from just changing the question, which is not a minor thing, as you know, in this course. Changing the question to one that we can answer is probably the best thing to do. But sometimes inside the data, you can find a subset of the data that's closer to the counterfactual. And maybe some of the data is so far from the counterfactual that it won't be of use, and in fact, it will induce more model dependence. And if we can only prune away those data and just keep the data that would be informative for the question of interest, that's what we'll focus on. So right now, I'm going to talk about matching to reduce model dependence right here. And then that will be in a generic way, where we're just going to understand matching as a specific way to prune observations away. And then exactly how we prune them away, we'll do that afterwards. That's the three methods of matching that come afterwards, and then problems with the most commonly used method of matching called propensity scores, and the matching frontier, which is an even more advanced method of matching. So first we'll do it conceptually, so you understand what it is, what to go after, what to focus on, how to think about matching and matching methods. That's what we're going to talk about for the rest of this presentation. And then the next one we'll talk about specific methods that you'll use in your research. Okay. So for readings, for all of this, I would ask some questions and then hear some answers. In each of these were the readings that we developed from this class, for this class, and around this class. So first, with my two co-authors, Stefano Iacus and Beppe Puro, we wrote the PA paper to try to answer the question, do powerful methods have to be complicated in the context of matching? Because one of the great things about matching is conceptually, as you'll see, it is very simple. It is very straightforward. For every treated unit, you look for a control unit that has the same values of all the explanatory variables, and anything that doesn't match, you just throw it away. Of course, you can't match exactly very often, and so then there's more and more complication in how matching methods work, and it doesn't much make sense to have a method that was designed to be simple but has layer upon layer of complication on top of it, and so it's not simple in the end. So what we did is we designed a method called coarsened exact matching that we will get to in the next set of lectures, that is very, very powerful, which we prove, and is exceptionally simple and easy to use and apply in your research. Next question is the most commonly used method of matching is actually called propensity score matching. You may have heard of it. You may have seen it used in lots of articles. A couple of years ago, we checked into it, and it was used in more than 140,000 articles. It sounds sort of magical. The idea is you can't find an observation that matches all 20, let's say, explanatory variables as the one in the treated group, but is in the control group. And so what you do is you project that 20-dimensional space down to one-dimensional space, and you match on that one thing, the propensity score. It sounds magical. It sounds too good to be true, and we show it is. And so Rich Nielsen, who took this class, he and I wrote this paper, came out of this class, came out of our work together. Rich is now a professor at MIT. So that was a PA paper. Then it is often asked whether, or actually, a better way to think about it is matching methods are either designed to reduce the imbalance between the treated group and the control group, or there's another thing that you have to actually do, which is make sure you don't prune away too many observations. So some of the methods make sure that you prune away the smallest number possible, and then you check to see whether you've achieved any balance. And others try to increase the balance or reduce the imbalance as much as possible and hope that you haven't thrown away too many observations. It makes sense, since we're trying to optimize two things, that we optimize them together. And so Rich Nielsen and I, and also Chris Lucas, who also took this course and is now a professor at WashU in St. Louis, wrote a paper on the matching frontier, which addresses both of those at the same time. Finally, current practice, which is matching as pre-processing, is incredibly convenient. The idea of pre-processing is we just spent a whole lot of time learning about modeling. We'd write down the statistical model and then write down the likelihood function and the log likelihood function and all that stuff, right? If I told you, here's how to do all that stuff, and you practice it and you do all the problem sets and all the other stuff that I had you do, and then I told you, you know what, to deal with model dependence, we have to do all that over again, I think you might kill me. So instead, I don't want you to kill me, and I don't want you to have to redo all of that, because that stuff is really useful. Instead, what we're going to do is we're going to treat matching as pre-processing. You take your data set, you prune away some observations, and then you do what you were going to do originally. You're going to do what we learned originally. And so that's a tremendous convenience. Unfortunately, it violates all statistical theory, so sort of a bummer. However, there's no reason why we have to go with that theory of inference. We can change the theory of inference to another perfectly legitimate theory of inference that is more useful for us, more convenient for us, and much easier to use. And so, again, with Stefano and Beppe, we came up with a new theory of inference for matching methods in causal inference. Okay, so I'm going to, in different orders, I'm going to go through these papers. You can look at them. They, again, came out of the class. They contribute to the class, and I recommend them. Some of them we've assigned to you. Matching helps reduce model dependence. That's the thing we're going to focus on. Here's a figure that I'm going to build piece by piece, which comes from a paper also in political analysis. This one is with 3 of my former students who also took this class. Dan Ho, who's now a professor in the Stanford Law School, Kosuke Emai, who's a professor at Harvard, and Liz Stewart, who's a professor in public health at Johns Hopkins, and Dean as well. So we have a graph here. On the horizontal axis is education, and on the vertical axis, we made up all the dots in this graph, so I didn't even choose a specific variable here. It's just the outcome variable. In any event, there are some treated units and some control units. And so the idea here is the horizontal axis, education, is a control variable. The treatment variable is T versus C. Right, that's the thing that we care about. T is a 1 and a C is a 0 for the treatment variable. And the outcome is the outcome variable. So, we want to know what is the effect of this treatment versus control on the outcome controlling for education. How do we do that? What we might do to begin with is build a model. So what's a simple model that we can start with? Linear regression. So in linear regression, we can run a regression of the outcome on treatment versus control and education. So that's the way we might start. And I can plot those results on the graph. I have one line for t equal 1 and one line for t equals 0, but color-coded to the units. So the causal effect here, if the regression is right, is holding constant education, which goes the horizontal way. If we go from t equals c, blue, to t equal t, or 1, red, then the causal effect is positive. So whatever that treatment variable is that we made up, the effect goes up. Okay, so that's the idea here. Well, what if the analyst actually wants the effect to be negative? I mean, what are you supposed to do, right? Well, you could look at this and you could say, you know, it's not, maybe the data don't fit the model so well, so really theory suggests that we should have a quadratic term. So instead of running regression of the outcome on the treatment variable and education, we'll add another variable, which is education squared. And so if we run that, it looks like that. And so instead of the linear blue line going up to the red line due to the causal effect, we look at the quadratics and it goes from the blue line down to the red line. So now this is much more convenient for the analysts because the analyst can choose whether to write up something that's a positive effect or a negative effect. It's much more convenient. And of course, this is a fantasy world, just so you know. All right, so but what is this? This is model dependence. This is the definition of model dependence. Usually we don't have a precise justification for whether it should be exactly linear or quadratic. So we have to decide, we might just choose one model, but that's sort of hard to do. The problem is we have model dependence. How are we going to deal with this? So let's get rid of those regression lines. Matching, which is a method that I will describe to you in some detail in the next set of lectures, will basically prune away some observations. If we apply a matching method to this data set, it will prune away those observations, the ones that get grayed out. See that? Okay, so they get grayed out. Now, on the remaining data set, let's rerun the regression. First, we'll run the linear regression. And then that's what we get. Now the causal effect from blue to red is basically 0. Right? Because there's almost no difference between those lines. They're plotted almost on top of one another. If we want to run now the quadratic regression in order to check for model dependence, that's what I'm looking for, I can take this thing and I don't need to click on it because the quadratic is also on the same graph. You can see it on the same graph because over on the right-hand side you see it splits just a little. So basically, what we found here is that the linear regression and the quadratic regression are giving almost the same results. So we've eliminated the model dependence in this subset of the data. So that's pretty interesting, right? The causal effect now has changed. It's 0. That needn't happen. Sometimes it happens, sometimes it doesn't happen. But it is a much more reliable causal effect. It's not going to be the case that somebody's going to come along and decide to make a minor tweak to the model and get a very different result. So that's a terrific result of matching, reducing model dependence. Okay, so let's take a step back and understand what are the problems that matching solves. Well, without matching, you wind up with imbalance between the treated units or the treatment group and the control group. When those things differ, then you get model dependence. Because when they're different, then what you need to do somehow is control for that difference, right? And you control for the difference by modeling, right? So that's the thing. So if you have to have a model, you potentially have model dependence. So imbalance leads to model dependence. If there's no imbalance, there's no need for a model to adjust. Model dependence, since researchers are not going to present every possible model, leads to researcher discretion. And even if a researcher is as honest as a researcher can be, the researcher is human and therefore biased. We know that. We know that humans tend to bias things, even imperceptibly small decisions in favor of their own prior hypotheses. Okay, so that's the problem with when you don't have matching. Now hold on a second. Why does it lead to bias? Okay, let's take a special case. Suppose we have 50 randomized experiments, every single one of them is perfectly set up so it fits the ideal experiment that I described some time ago, or even the even more ideal experiment, right? Everything's right. There's no measurement error. There's no missing data. There's a random selection from the population. There's a random assignment to the treatment units. The effect's large. No problem. We don't have to run a linear regression. We can take a difference in means, linear regression. Any one of those things should give basically the same answer in a great randomized experiment. But suppose we had 50 randomized experiments, and you get to choose one of them to present on the basis of the results. So that estimator, remember an estimator is some function of the data. If you as the human being are stuck into there as part of the estimator making a qualitative choice on the basis of the outcome, then that whole thing that is the estimator is actually biased. In fact, if you choose based upon your definition of plausibility, that is even worse, because you'll look at those answers and you'll try to attach them to your prior knowledge and things like that, but it will just be impossible to not attach them to the results that you want. We know that from very well conducted psychological experiments. So what do you do? Well, you could put a lot of effort into it, but we know that conscientious effort doesn't avoid biases, right? So if you try to avoid the biases, we know it doesn't help. Najim Benaji, who's in our psychology department, has studied this in quite some depth. And we just know that putting in intentional effort just doesn't do it. Okay, so what do you do? Well, it's not clear, right? Like how are you supposed to fix this? The problem is, the reason why you can't fix the bias yourself is we don't have access in our mental processes to know when we're biased. I mean, if we're practicing diving for the Olympics, we get some feedback and we do better. When we do badly one time, we learn what it is, we do better. We keep doing that, we do better. If you keep making decisions and you have no idea whether they're biased or not, then you're just more likely to not change anything if you don't get feedback. So you just can't learn without feedback. Okay, wait a second. Suppose that we take an expert in this field, someone who knows about all this stuff and is really an expert. Who am I talking about? Basically me and you, okay? So we take an expert and we apply the same psychological experiments to them. We try to figure out the biases and all that stuff. They're choosing one of their results from a whole set of models. What happens? Well, experts overestimate their ability to control their personal biases more than non-experts. And the most prominent experts, and that is you and me, or me at the moment, are the most overconfident, okay? So that's a bummer. Okay, one more try. Okay, we take experts and then we teach them about these results, right? We say, even after you become an expert, you will be biased and therefore correct for your biases. So doesn't that work? Well, as Nobel Prize winning psychologist Danny Kahneman showed, and I quote, "Teaching psychology is mostly a waste of time." That's a great quote, especially when the political scientists and sociologists and economists want to get more positions from the administration, more faculty positions. We try to show them that. But of course, that's a joke, because this teaching psychology is mostly a waste of time applies to this kind of case in which we're trying to teach away biases that it's not really possible to learn because you don't have access to your own mental processes to know when you're biased. So you need something else. What do you do actually? Okay. Well, one way of thinking about this is a great example I heard from the late Richard Hackman, and his story was bias in orchestra tryouts. So what happened was, it was tryouts for the violin. And so they'd have a whole bunch of violinists come line up, and everybody would play the violin, and there'd be a bunch of judges in the front, and the judges would judge the violinists. The men won every time. Okay, now, is that really fair? Maybe the men are better, okay. So then they decided, wait a second, maybe everybody knows that they're biased. So they tried to explain to the judges, you know what, you're just being biased. Don't be biased. Really think about it. We definitely want the best violinists in our orchestra, but do the best you can, okay? And try to avoid the biases. They did the same thing. Everybody comes up. Men won all the recitals. Okay, so what do you do next? So then they had this idea. let's put them behind a curtain. Okay, so they had them. They introduced a procedure. That's the idea, right? The judges don't know when they're being biased. They really think they're making the right decision by choosing what happens to be all the men. So they put a procedure in place that takes the discretion away from them. That's the idea. You remove the discretion to be biased, and maybe it'll be unbiased. So you put them behind the curtain, and then you have each one come right, and they're only listening. They're not watching, right? And what happens? The men won all the recitals. The men won all the recitals even though they couldn't see them. So what happened? So they're thinking and they're thinking and the researchers are thinking and thinking. And then what they say is, take off your shoes. And they made them all take off their shoes because you could hear high heels walking in differently than you could hear the men walking in. And they did it without shoes. And then the men and the women each won about 50% of the recitals. So it's a cool story, but the main thing about the story is you put the procedure in place to take the discretion away. Humans are great at certain things, and they're just, they're incapable of doing other things. Let's let them do the things they're good at. That's the idea here. So with matching, that's what we do as well. With matching, we eliminate the imbalance. So we have balance. When you have balance between the treated and control groups, there's no reason for the humans to run the model, and so there's no model dependence. Since there's no model dependence, there's no researcher discretion. They don't need to choose among different models or different sets of results, and there's no bias. So that's really great. In addition, this is basically a central project of statistics, which is automating away human discretion, right? Because you don't want the humans to be deciding things they're just not good at. So what's matching? Well, let's do it a little more precisely. The details of how you're going to use it is going to come in the next set of slides, but I want you to have an understanding of why it's there, what it does, and what it accomplishes, really, but with more precision. So we're going to have a dependent variable, y of I, as we always have. T of I is going to be the treatment variable, 1 for treated, 0 for control. And xi is going to be a vector of a whole bunch of covariates, pre-treatment confounders, or confounders, pre-treatment variables, covariates, whatever you want to call them. The treatment effect for treated observation I is going to be TE, treatment effect. And that treatment effect is going to be defined as the difference between the two potential outcomes. That is the definition of causality, or a causal effect. One of these is observed, and one of these is unobserved. The first one is observed because I said right above here that this is the treatment effect for treated observation I, and treated observation I is observed. So y of 1, where 1 means t equal 1, so it's the treated value, and y equals 0 otherwise. The thing is that since the first one is observed, we don't need the potential outcome notation, so I'm going to get rid of it. And then there's really only one thing missing. So if we could fill in that one thing, then we would know the treatment effect. But of course, for the same observation at the same point in time, it's not possible to go back in time and not apply the treatment to this unit that actually did get the treatment and see what would happen. So y of 0 will forever remain unobserved, and causal effects will always have to be the subject of inference. So that's the story here. We're going to estimate y of 0 with another. I mean, the real question is, how do you get y of 0? Because you can't see it. So the idea of matching is we're going to estimate y of 0, which is forever unobserved, with another observed unit that is a control unit that has received control. That is t of I equals 0, but has the same values or nearly the same values for all the other explanatory variables. So that's the idea. That other value is going to be y sub j. It's a different unit. It's not y sub I. But that y sub j is going to have x sub I, that is the same x as over here, equaling approximately x sub j. And so that's how we know it's the same. Now, if you have the right variables, you need the right variables. If you have the right variables that really characterize the meaning of what that unit is, then turns out you can use that and swap that in, swap that matched value in to estimate the treatment effect. Okay. So from this, let's look at the quantities of interest. SAT is the sample average treatment effect on the treated. It is the quantity of interest we've talked about before. It's just the mean of a whole bunch of treated units for just the just the treated units, just the T of I equaling 1. So that's the sample average treatment effect on the treated. Then there's one other quantity of interest beyond the ones I've given you. And why is that? Well, in this case, we're going to take all the treated units, we're going to find another control that substitutes for the one that's here. But suppose there's a case in which there's one treated unit and there's no control that's anywhere near that treated unit, right? Something like in the case of peace building success. What if there's just nothing there? Well, we don't want to make an inference on the basis of that because it's just going to leave a lot of model dependence. So sometimes we can save the day. We can make an inference that is a subpart of the data set and use that. So we can prune away not only the controls that don't get matched to the treated units, but we can prune away some treated units. Now, if you prune away some treated units and the causal effect is different for each observation, which it might be, then we're going to change the quantity of interest. And so that's not necessarily a bad thing, but you have to know you're doing it. So we're going to define something called the feasible SAT, or FSAT, or FSATs, if you like. And the idea is you prune away the badly matched treated units too, you change the quantity of interest, and then you pay close attention to the fact that you're not estimating the causal effect for everybody in the population, but only women between 18 and 24 in Wyoming, or whatever it is the subpopulation is. Matching is, as I said, a big convenience because we're going to follow the matching induced preprocessing with whatever statistical method you'd have used without matching. And then why does this work? Well, pruning non-matches makes the control variables matter a lot less. It reduces imbalance. The imbalance reduces model dependence. The reduction in model dependence leads to less need for researcher discretion. And since the researchers don't have discretion over things that they don't know anything about, can't evaluate, there's less bias. So next thing we need to do is evaluate the reduction in model dependence. And I'm going to show you how to do that. I'm going to show you at least the consequences of doing that in a real example, and then we'll show you how to do it afterwards. So this is an example from Dan Carpenter. He's a professor in the Harvard Government Department. He wrote a great article in the American Journal of Political Science in 2002. And he was interested in the effect of Democratic Senate majorities on FDA drug approval time. And what his hypothesis is that when the Democrats control the Senate, the FDA takes longer to make decisions. That's a really important subject, of course. The Food and Drug Administration is the FDA. So he collected a novel data set of 408 new drugs. 262 were approved. And remember, he's measuring duration to approval. But some of them had not been approved yet. In fact, 146 were still pending. And so the duration there are at least as long as it took him to observe them, right? And we don't know how much longer the FDA will take for those. And so they're pending, or what we would call censored. We could apply the model that we described earlier, the exponential model with censoring to this, but with these confounders, right? So the pretreatment covariates, right? So we could apply that model, but he applied a more sophisticated model called the log normal survival model. But the concept is pretty much the same thing. So we're gonna follow along and use the same thing. The quantity of interest is the causal effect of the Democratic Senate majority on FDA drug approval times. And the cool thing for us, for our methodological purposes, is that Dan, in his article, to his incredible credit, noticed that his results for this variable, he had lots of other things that he was studying, were very not what he called not robust, or what we would call highly model dependent. And so he wasn't willing to base his conclusions on that particular result, which is actually pretty important. And it's great that he did that and he noticed it. So we don't have to detect model dependence because he already did it. Now we're going to see whether we can do something about it. So we did matching. I'm not going to tell you the method of matching. I'm not going to describe the matching. I'm just going to describe the results. So the results were, when we applied matching, from his data set, we wound up pruning 49 units, 2 treated units and 17 control units. So two of the treated units are examples that made this FSAT rather than SAT, the feasible SAT. Okay, then we want to show model dependence, not substantive results, but model dependence. Normally, you run one analysis. For our purposes, I want to show that there's a lot of model dependence, or how much model dependence there is, so I want to run a lot of models. Where are we going to get the models from? So we took all of the 18 confounders, and we included, the confounders and squared terms and interactions, lots of different things. And we ran, like all different subsets of those variables. And so lots and lots and lots of different specifications within the same model. For every one of those, we calculated the quantity of interest. For every one of those quantities of interest, we put them in a big basket. And at the end, we had 262,143 separate quantities of interest. And from that, we're going to look at how diverse they are, because how much variance there is in them, because that's our measure of model dependence. So it's the variability in SAT across those specifications that gives us, and just to emphasize again, if you're going to run the log normal survival model for some particular application, you wouldn't run 200,000 analyses. You wouldn't only normally need to, you would run one, but for our purposes, we are. Okay, so here's the results. The horizontal axis is the average treatment effect. It's how much longer it took. And this is, in fact, it took, about 53 fewer days or something like that. This was Dan's estimate, but he didn't want to pick that because there was a lot of model dependence. You can see the model dependence here. This is pretty much what Dan saw in a somewhat more formal way. This is a histogram of the 262,000 SAT results. Okay, so there's too much variability here to really conclude a lot. So we ran matching. After we ran matching, what did we do? Well, we pruned the data set. Then we did exactly the same thing. We ran 262,000 regressions again, or log normal survival models again. And in every one of these, we ran the same analysis. We plotted another histogram. Note, and here's the results. Note how much narrower the variance is here. Within this range, it doesn't much matter what the answer is, right? Because they're all pretty similar. So in that sense, even if a human being is going to be choosing one of those models rather than the other, they're not going to be biased, because it doesn't much matter which model they choose. So that's the effect of matching in reducing model dependence. I'll give you one more example here, which is from Jeffrey Cox, also another interesting article, also from the American Journal of Political Science in 2002. His estimate of his causal effect, which I'm going to skip the substance, was right here. There was a lot of model dependence in his results. This is the distribution of it turned out that he had fewer covariates, so we wound up with 63 possible specifications. This is a histogram of those 63 specifications. It goes from negative to positive. You really can't conclude very much if you consider all those as plausible models. They're not necessarily, of course. We just included a whole lot of them. But we didn't want to use plausibility as a measure, because we know that our decisions would be biased. Then we narrowed it down. We took the data set and narrowed it down by pruning some observations via matching, and then reran the 63 analyses again, replotted the histogram, and now the histogram is here with a much smaller variance. So now again, there's much less model dependence if you do matching. Okay, so let me talk about the assumptions necessary to justify the current practice of matching. Then we'll stop for today. There's the existing theory of inference, which is, unfortunately, if you apply the existing theory of inference, you can't apply matching as preprocessing. So you pretty much have to stop. So we're going to introduce a new theory of inference, as I said earlier, that it's going to be okay. It's a perfectly legitimate theory of inference. We basically changed the question as to what it is we're after, and matching as preprocessing fits very well within this framework. All right, so the existing theory of inference, I'm not going to go through the details of exactly how this works, but I'll give you a feel for it. or a feel for what the consequences are. So the framework of this theory is simple random sampling from a population. So the idea is that when you run an analysis, we have to make an inference to something. They're imagining that your data was collected by simple random sampling. That might be right. Exact matching, the way that their analysis works is you assume exact matching. If you assume exact matching, then the theory works. That is, you assume the data is selected by simple random sampling, no stratification or anything like that. And then if you can apply exact matching, if there are enough exact matches in there, then this would work. But that's rarely possible. If you have enough covariates and they're sufficiently informative, then typically you're not going to find a treated unit that has the same value on all of the covariates as a control unit. It's just not going to happen, at least not often enough. So the assumptions are of this theory are unconfoundedness, which basically means you have the right variables. Once you have the right variables, the treatment effect and the potential outcomes are unrelated. In particular, the way we've set it up here is there's only one potential outcome that's unobserved, which is y sub 0. And treatment and that potential outcome are unrelated after you condition on x. That makes sense, that's plausible, if you have the right x's, basically. If you don't have the right x's, then it's a problem, and so that's the idea. You don't want to only give the treatment to people who are healthy and the control to people who are not healthy, because then even if the medicine doesn't have any effect at all, it'll look like it has an effect. So that's the assumption. There's also a common support assumption, which is the probability that a unit receives treatment is not 0, okay? And it's not 1. That means that when you have a person or a unit that receive treatment, it's at least possible that they could receive control. That's the idea. If it's not possible that they could receive control, then the whole idea of causal inference doesn't make any sense, because the causal effect itself isn't even defined, because the potential outcome y of 0 doesn't exist for us to estimate. So common support makes good sense if we're looking at the effect of pregnancy on some outcome and we have men and women in our sample. Well, the causal effect for men, it's not even defined, right? Because to imagine what would be like if a man were pregnant, I know some of you have imagined that, but that's not really relevant here. Okay. Now, suppose you can't do exact matching, you can only do approximate matching. This theory has been developed for that purpose, so that's great. But if you follow down that path, you can't use matching just as pre-processing and do anything that you were going to do previously. What you have to do is use a specialized bias correction procedure and a specialized variance estimation procedure. So you can't simulate the way that we've shown you. You can't calculate the variance covariance matrix the way we've shown you. You can't calculate the maximum likelihood estimates the way we've shown you. All of these things have to be adjusted in some way. And so that's not necessarily a bad thing, but it requires a lot of extra work and frankly for not a lot of advantage. And so we can get rid of all that by just changing our theory of inference. How's this going to work? Well, instead of simple random sampling, we recognize that most data sets, actually even surveys, they don't use simple random sampling. Most of them use stratified random sampling. So now we're going to imagine that under this theory that's well-developed mathematically, just like the original theory was well-developed mathematically, that we have stratified random sampling from some well-specified population. We're going to define our strata. So one stratum, the way we get a stratum is we take our explanatory variables. Let's first imagine that they're all discrete. Then take all possible combinations of them. It's called the cross product of all of them. So if we have men and women and black and white, you have black male, black female, white male, white female, etc. So that's all possible combinations. And then each of those is one stratum. Well, what about continuous variables? Well, our theory of continuous variables is that most of them, not all the time, but most of them actually have logical discrete points in them. So if you have if you have income, there's a discrete point at which you're below the poverty level, or a discrete point at which you're due certain benefits, or a discrete point at which you have to pay taxes. If you have years of education, that's or minutes of education, that's essentially a continuous variable. But there is a big bump that happens when you get a high school degree or you get a college degree. In fact, very frequently we take years of education and just code it as high school, college, graduate school, et cetera. And so I think we understand very frequently when we do data analyses about grouping into these categories. So as it says, we wouldn't match a college dropout with a first-year graduate student. Those are very different people, even though the number of years of education may be very similar for the two. So discretizing the continuous variables is an assumption that we're making, but we think it's reasonable substantively. Okay, so there's some assumptions that we have to adjust here. Instead of the unconfoundedness assumption, we're going to assume unconfoundedness within the strata. So within each of the strata, it's called set-wise unconfoundedness. And instead of common support, we're going to assume set-wide common support, which is common support, but within the strata, conditional upon our strata. This fits all common matching methods and does not require asymptotic. So you don't have to assume that you have an infinite sample or anything, or a sample going to infinity or anything like that. There's easy extensions for this theory to multi-level models and continuous variables and mismeasured treatments. If A is too wide, if you have strata that are too wide, then you may capture too many things. If n is if you wind up with too small an n, there's ways of adjusting, but you have to adjust by adjusting the strata. We will talk about that and be very precise about it so that we can use it in practice when we get to CEM, coarsened exact matching. Okay, so that's all for today. Next time we're going to talk more about the specific methods of matching. We're going to talk about 3 specific commonly used methods of matching, and we're going to show you exactly how to use this in practice so you can use it in your research. Okay, thanks for listening. See you next time.